Dear students, today we will discuss solar radiation geometry. So before we start solar radiation geometry, let us summarize what we have discussed in the last lecture. So we are discussing about different instrument used for measurement of solar radiation and duration of sunshine hours. So we have learned how these different instruments work. So for measurement of normal radiation, we have to use perheliometer, and for measurement of global and diffuse radiation, we have to use pyranometer, and for measurement of duration of brightness of the sun, we have to use sunshine recorder. So these three instruments are very important for measurement of radiation parameters. Also we have studied the different units like Langevin, what is watt per meter square. So how these parameters are represented. If we are dealing with instantaneous values, we will use only Ig if we are interested for global radiations, then Id in case of diffuse radiations, then In is for normal radiation. And if we are interested about hourly average, then we will put a bar on the top of these parameters. And sometimes we are also interested to know the variation of radiations in daily basis. So under that conditions, what we are going to use is Hg, Hd, then Hn. So again, if we are interested to know the average values, say for example monthly average values, if we are interested, then monthly average of daily radiation, if we would like to know, then we will use a bar on the top of it. So these parameters we have learned in the last class. Also we have studied the radiation patterns on a clear sky and on a cloudy sky. So in cloudy sky, a lot of peaks and valleys are observed, but in case of clear sky or cloudless sky, so these variations is something like this. So normally maximum radiation is observed at the noon. So this is about 12 noon. Okay. So these parameters were studied, and also we have studied the radiation map. So sometimes radiation maps are used to know the radiation spectrum of a particular region. So we have studied, for example, for a country like India. Now come to our today's lecture. So radiation geometry we need to understand very clearly, then only we can do a lot of calculations which is required for estimation of global radiation, diffuse radiation or normal radiations. So first thing we must know what is beam flux and equivalent beam flux. So if we have to know this beam flux, suppose this is the earth's surface and solar radiation is coming. So solar radiation may come from any direction. Okay. So this may be In, this is the beam flux, or I should write IBN. IBN is a beam flux. B stands for beam radiation. So this is the beam radiation falling on a particular place. So if I am interested to convert to the equivalent beam flux, then what we need to do? Then this is the orientation of the radiation, and then we have to draw a line which is normal to the surface. Okay. So let this angle be theta, and this is IBN. So equivalent value will be, equivalent beam flux will be IBN cos of theta. So for all the calculations we need to do this. So this is nothing but this is normal to the surface. So solar radiation may come from this side also, maybe from this side also. So we have to convert it with respect to the normal to the surface. So, that is why it is called equivalent beam flux. So, this theta is a function of many angles like declination, tilt, solar azimuth angle, altitude angle, and so on. So, we need to understand how this cos theta is varies with respect to different angles. So, let us see what are different angles are present. Angle of incidence, this theta what we have studied in the last slides. So, this angle is something like, this is the IBN, this is the surface, this is the solar radiations, and this angle is theta. Okay. So, for example, here what we are considering, this is the horizontal surface. So, this is the beam radiation falling from the sun and striking on the surface which is horizontal, and this is your normal to the horizontal. This is normal to the horizontal, normal to the horizontal. So, there are some cases where we have to study when it is inclined. So, inclined at an angle say beta, and beta may vary. So, we will learn how it varies. So, this angle is beta, this is known as slope or tilt angle. So, first case what we have studied, that is horizontal surface, and second case it is inclined surface. So, if it is inclined, then our things will be something like this. This is the normal, and solar radiation may be here. So, this is your normal to the horizontal surface. Okay. And already we have studied what is zenith angle. Okay. If it is horizontal surface and normal to the horizontal is this, and solar radiation is falling here. So, this angle is theta z. So, if we consider a inclined surface, and if solar radiation is falling here and normal to the inclined surface is something like this. So, this angle will be theta, but when we are concerned about normal to the horizontal, and when this sunbeam makes an angle with the normal to the horizontal, that is called zenith angle. So, this is theta z. Okay. So, this thing should be clear when we draw many angles, and with time you will understand the importance of those angles and how these angles are different. And latitude, let us learn what is latitude. Okay. So, this slide shows different pictures of to represent latitude and longitude. So, these parallel planes, these are the parallel planes parallel to the equator are latitude, and if it is perpendicular to the equator are longitude. So, this latitude or longitude are used for coordinate system. Of course, we need elevation as well to specify the coordinate completely. So, here if we have to define latitude, say for example, let us consider a place here. Okay. I am interested to know the latitude of that location. So, what I will do, I will draw a line from this location to the center of the earth, and we will project this line on the equatorial plane. This may be our equatorial plane now. So, this will be something like this, and this angle will be phi. Okay. Of course, we can write this, and we can have this observer's meridian. Okay. This may be observer's meridian or meridian, and this is the position of the observer, maybe position of the observer. Okay. So, hope you understand this. So, this is the position of the observer, and we will connect the center of the earth to the position of the observer, and we project it on a equatorial plane. Okay. This may be P, you can say this may be Q, and this angle is phi. So, this phi is nothing but latitude of the location. So, this phi we need to calculate in many of the occasions for calculations of many radiation parameters. And also you can see these lines are longitudinal lines. Okay. So, as you can see this is the prime meridian where our longitude is 0, and then we can see the coordinate system, and this is the equatorial plane. What we have explained here, this is the equatorial plane, and this phi varies from minus 90 to plus 90. This is the variation of phi. Okay. So, let us discuss the other angle like declination. So, what declination signifies or defines like the angular displacement of the sun from the plane of the earth's equator. So, if we have to present or have to define, let us draw this sun here and maybe earth here, and we will connect the center, and maybe we will draw this as north south, and of course, we will have east and west here, and this is equatorial plane. This is equatorial plane, and if we have to define declination delta. So, what we do, this is sun, this is earth, we connect the center of the sun and center of the earth, and this line will project on the equatorial plane. Okay. So, this angle is delta. So, when we connect center of the sun and the center of the earth, and that line will project on the equatorial plane, and that angle is known as delta or declination. So, declination is very important, and how this declination varies we will discuss now. So, for example, if we have to show the variation of declination throughout the year, that is the variations in sun's declination, we can study. So, maybe we can put it here 0, then we have this may be minus 10, this may be minus 20, and this may be minus 30, and here we will have 1, 2 and 3. This is maybe 10, this is 20, this is 30. Okay. And we will have this maybe June, this is maybe December 21, and we need 1, then we have 2 and 3, we need 4. Okay. Okay. So, how this will vary? December 21, then we have March, I will write M 21, this may be June 21, then we have September 21, and we will have again December 21. So, declination will vary. So, this is delta, okay, and this is the month, and this will vary. So, this will be minus 23.45 here, 23.45 will be somewhere here, and in March 21 it will be 0, and June 21 it will be plus 23.45, it will be here somewhere, and in September 21 again it will be 0, and because these two are equinox, winter equinox and summer equinox. So, this is winter equinox, this is summer equinox, and here again it will be minus 23. Okay. So, if we plot this variation, this will come something like this. Yeah. So, variation of the sun's declination is something like that. So, if we have to find out the declination of any day, we can calculate it by using delta is 23.45 sine of 360 by 365, then 284 plus n. N is the nth day of the year. Okay. So, we can use this plot, or we can calculate by using this delta if we know which date we are doing the calculation. So, n is the nth day of the year. So, as you can see from this plot, this variation of delta varies from minus 23.45 degree, which appears in December 21, and maximum is plus 23.45, which appears in June 21. Okay. So, that is why this variation is from minus 23.45 to plus 23.45. So, what we can summarize here. So, declination is very important. It defines the angular displacement of sun from the plane of the earth equator. So, this is the earth equator, plane of the earth equator, this is the delta, and this is the angular displacement. And also another way we can define, this is the angle between the line joining the center of the sun, the center of the earth, and projection of that line on the equatorial plane. That angle is nothing but delta or declination, and declination varies from minus 23.45. So, minus 23.45 appears in December 21, and maximum is found to be plus 23.45, which appears on the day of June 21. And also we can calculate declination, and this will be in degree, or I should write in degree. Okay. So, delta is 23.45 sine of 360 divided by 365 in bracket 284 plus n. So, n is the end day of the year. So, for example, if we have to calculate the delta for say January 1, So, n will be 1. So, under that condition you can calculate what will be the value of delta. Or for example, if we are interested for February 1, then what will be n? N will be 31 plus 1, it will be 32. So, if we substitute the value of 32 here in place of n, then we will get the delta for February 1. So, that is how we can calculate the declination on a particular day. Now, let us study hour angle. So, hour angle is very important. So, we need to calculate local apparent time for calculation of hour angle. So, hour angle we represent like omega. So, it represents the angular displacement of the sun east or west of the local meridian due to the rotation of earth on its axis at 15 degree per hour. That means, it signifies like 1 hour is 15 degree, or 15 degree represents 1 hour. Okay. So, if we plot it like this way, and maybe you can write this, and we can write a line here. Okay. So, this is omega is 0, and this is called solar noon at 12:00 hour. And if we divide, maybe this is 11 or this may be 10. Okay. So, this angle is 15 degree. Okay. When this difference is 1 hour, so 1 hour is 15 degree, this is also 15 degree. Okay. Total hour angle will be here, this angle will be 30 degree. Okay. So, this way we can measure, and it measures the angular displacement of the sun east or west of the local meridian due to rotation of earth on its axis at 15 degree per hour. Okay. So, 1 hour is 15 degree. We will do a lot of calculations how to calculate omega, and what happens in case of sunset and what happens in case of sunrise. So, all the things we need to calculate, and here we can say omega is positive in the morning, this part is forenoon, this is forenoon and this is afternoon. In case of forenoon, omega is positive, for afternoon omega is negative. We normally, these sign conventions normally considered. Okay. And here omega is plus 90 at 6 hours solar time, and this will be omega will be minus 90 at 18 hours, and this is also solar time. Okay. So, what we need to learn here, that is the solar hour angle is very important for solar calculations, and 1 hour is 15 degree. Okay. And how we have defined this hour angle, like it is a angular displacement of the sun. Okay. And it varies from minus 180 to plus 180. Okay. So, we will learn details when we solve some numerical problems related to this hour angle. So, now let us learn something about solar azimuth angle and inclination angle. So, this solar azimuth angle is represented by gamma s, and inclination is alpha a. Okay. And this is related to horizontal surface. Okay. Let us draw one horizontal surface or something like this, and maybe we will find out the center here. This is north, this is south, east, and then we have west. Okay. So, normal to this horizontal surface is something like this. Okay. And solar radiation is falling from here. Okay. So, this angle is always known, this is zenith angle theta z. Okay. Please remember that this is horizontal surface. So, we are not talking about inclined surface, this is a horizontal surface, and normal to the horizontal is this is normal to the horizontal surface. Okay. And this is the incident beam radiation. So, if this is projected here, and of course, we need not to explain to this. Okay. So, maybe we can extend this somehow, and this angle is gamma s, that is solar azimuth angle. So, this angle is angle made in horizontal surface. This is due south, So, this is the angle in the horizontal plane. So, what happens? This is sun. So, sun beam radiation is falling on this horizontal surface, and we have drawn this normal to the horizontal here. This is the normal to the horizontal, and this angle is always a zenith angle. And then, if we project this beam radiation on the horizontal plane, and this angle is this projected line and the line towards due south, this angle is gamma s, and this angle is inclination angle or alpha A. Okay. So, this is the angle on horizontal plane between the line due south and the projection of the sun's ray on the horizontal plane. This is the horizontal plane, and it is positive when it is measured from southward west. Okay. So, it is positive when measured from south towards east. Okay. So, please keep in mind that these things are happening in horizontal surface. So, we are not talking about the inclined surface. So, when we deal with inclined surface, then we will talk about surface azimuth angle, right. So, this angle gamma s is the angle on a horizontal plane between the line in due south, is the due south, and the projections of the sun's ray on the horizontal plane. Okay. So, this is important, and this angle is inclination angle. Okay. So, these informations are also required while calculating this solar radiation parameters. Now, let us learn about solar azimuth angle. So, this azimuth angle is important because most of the time we will be dealing with this gamma, and this gamma is nothing but surface azimuth angle. Okay. So, this is related with inclined surface. So, let us make an horizontal surface, and maybe we will take some kind of this, and maybe we can have this kind of inclined surface. So, this maybe this angle is beta. Okay. So, normal to the horizontal we can draw this way, and this normal to this inclined surface will be something like this. Okay. So, solar radiation, normal solar radiation is falling here. So, this angle is theta, but this angle is theta z. Okay. So, now I think you can understand what is the difference between theta and theta z. Now, if we project this normal to the horizontal surface on this horizontal plane, and this angle is gamma. Okay. So, how we can define this? So, this is sun. So, it is the angle in the horizontal plane, this is the horizontal plane between the line due south, this is due south because this is N, this is S, this is east and this is west. So, this is due south, okay. And the horizontal projection, this is the projection, okay, of the normal of the inclined surface. So, this is the normal of the inclined surface, and this is the projection. So, this angle is gamma, which is nothing but solar azimuth angle. So, this angle is very very important because most of the time we are going to use this gamma for our calculations, and variation of gamma can be seen, it is minus 180 to plus 180. Also, there are certain cases like slope towards the south. If we say slope is towards the south, then value of gamma will be 0, and slope towards the north will be 180, then slope towards the east is minus 90, slope towards west is plus 90, then slope towards the southeast is minus 45 degree, slope towards the southwest is plus 45 degree. Okay. So, these are different angles we need to understand, and we can use it for reduced calculations. So, slope is already defined. So, what is slope now? So, if we maybe we can draw again this surface, and maybe horizontal surface, and if we draw this kind of systems, okay, so this angle is beta, okay, or maybe if we draw this kind of system, if you consider horizontal surface and maybe one inclined surface, so this angle is beta, okay. So this is beta. So it varies from 0 to 180, and sometimes its beta is greater than 90. That means the surface has a downward facing components. So this slope also we learn, and let us combine all the angles and let us see how it look like. So again I will draw one horizontal surface, and will write this is the north, this is south, east and then west, okay, and we will draw this and that makes an angle. This is an angle. So this, if we say this is the angle, this angle is beta, okay, and this is normal to the horizontal, and we will have normal to this inclined surface. This is normal to the inclined surface, and we will have solar radiation will fall here, okay, and already you know this angle is theta, I will write here, and this angle is theta z, because theta z is zenith angle and theta is incidence angle. So the incidence angle already we have defined, and if we project it on the horizontal plane, okay, and we will maybe here, okay. So this angle is azimuth, surface azimuth angle is gamma, and if we projected this one here on this plane, and the kind of angle what we will get, this is solar azimuth angle, and this is alpha a, okay. This is your altitude or inclination angle alpha a, okay. This is sun, or you can write this one, because sun is radiating this beam energy and is falling on this inclined surface, okay. So now you can learn the different angles, like in this surface we have introduced many angles like beta, then theta z, theta, alpha a, gamma, gamma s, okay. So now what we will study, we will study the cos theta, how this cos theta is a function of many angles. So we are not going to derive the expression how these angles are related with cos theta, but finally we will use the result of this geometry. So how this cos theta is a function of different angles, okay. So as you understand, so briefly what we can discuss in these slides. So this is a horizontal surface, let me write, this is horizontal surface, and this is inclined surface, inclined, this is inclined surface, okay, and this is normal to the horizontal, this is normal to the horizontal surface, and this is normal to the inclined surface, normal to the inclined surface, inclined surface. Okay. So, also for your understanding, and this is a zenith. Okay. So, these are different angles involved, and this is the inclination. Beta is a slope, and theta is zenith, and theta z is zenith angle, and theta is incident angle, and alpha is altitude angle. Then gamma s is solar azimuth angle, and this gamma is surface azimuth angle. Okay. Now, I will relate this theta with respect to all these angles. So, how this can be expressed? I will write cos theta is equal to sine of phi, then you have sine delta, then you will have cos beta, then plus cos of delta, then cos of gamma, cos of omega, sine of beta, plus cos of phi, then we have cos of delta, cos of omega, we have cos of beta, minus sine of delta, cos of gamma, then sine of beta, plus cos of delta, then sine of gamma, then sine of omega, and sine of beta. Okay. So, this is an expression which relates cos theta with different angles. So, sine phi, okay, then cos we have this, and then we have, okay. So, this is maybe equation A. So, every time we need to do this kind of calculations, if we know this delta, beta, phi and omega, then we can substitute here and we can calculate what is cos theta, because on all the cases we need to find out what is cos theta, that is equivalent beam flux. Okay. This has to be calculated, right. So, now we will study different cases, like you can say these are special cases. Okay. What happens if beta is 0, what happens if gamma is 0, okay, what happens if beta is 90 degree. So, all those cases we will study, then later on we will solve numerical problems to strengthen your understanding. Okay. So, we will study some cases, maybe in case 1 for vertical surface. So, in case of vertical surface, that is beta is 90 degree. Okay. So, if we substitute beta value 90 degree in equation A, then what will happen? So, we will go back to the slide, and if we substitute beta is 90 degree. Okay. So, if we substitute beta 90 degree, so here we can substitute here. So, cos beta will be 0, okay, and sin 90 will be 1. So, this will be 1. Okay. So, this will retain, and here and this will be retained. Okay. So, this will be 1, okay, and then this will be 0, this part will be 0, means this expression will be 0, this will be 0, okay, and then this will be 1. Okay. So, if we simplify, then what expression we will get here? So, I can write, if beta is 90, then cos theta will be, it will simplify to a expression of something like this: sin phi cos of delta, cos of gamma, cos of omega, minus cos of phi, then sin of tan cos of gamma, plus we will have cos of delta, then sin of gamma, then sin of omega. So, this will be the expression. So, for a vertical surface beta is 90 degree. So, we can use this expression to calculate cos theta. Okay. This equation maybe we can name as B, and for horizontal surface where beta is 0. So, again we can substitute the value beta is 0. So, beta is 0 means here it will be 1, cos 0 1, then this part will be 0, this part will be 0 again, then this part will be 0, this part will be 0, and this part will be 1. So, if we simplify, then what expression we will get? We can write here cos theta will be sine of phi sine of delta plus cos of phi cos of delta, then cos of omega. So, this is equation C. Okay. So, this is the equation C. Okay. So, if the surface is horizontal, then we can use this expression to calculate cos theta. Okay. For inclined surface facing due south. Okay. So, due south means what we can do? We have gamma is 0 and inclined surface at maybe at certain angle beta. So, only gamma will be 0 here. So, if you substitute gamma, then we can simplify this and we can get an equation of something like this, sine of, or get an expression of something like this, sine of phi minus beta. Okay. Phi is latitude plus cos of delta, then you have cos of omega, and you have cos of phi minus beta. Okay. So, this expression we can name as equation D. Okay. Now, come to the case 4 for vertical surface facing due south. So, vertical surface means beta is 90 degree and due south is gamma is 0. Okay. 0 degree. Okay. I will write 0 degree and beta degree here. So, if we substitute this value, then this equation or maybe equation B will simplify something like cos of theta is equal to sine of phi cos of delta cos of omega minus cos of phi, then sine of delta. Okay. So, we can name this equation as E. Okay. So, in the last case, there are many more cases. So, as per my formulation, so for inclined surface facing due south, so here what happens? We have gamma is 180 degree. Okay. So, this is facing due north. Okay. So, our expression will be cos theta is equal to sine of delta, then we have sine of phi plus beta, okay. Then we have cos of delta, then we have cos of omega, then we have cos of phi plus beta. Okay. So, this equation will be something like this. Okay. So, this will be F. Right. So, these are the special cases we have formulated. So, at different conditions we can use different expressions, but straight away we can use the original equations, these equations which is good for all the cases. Just we need to simplify, we need to consider say for example, vertical surface beta is 90, for horizontal surface beta is 0. Okay. If it is due south, then gamma is 0 degree. So, that way we need to consider, and we can simplify this expression and we can get different equations. Okay. So, once we simplify it, then it is very easy to calculate the value of cos theta. Okay. So, now let us now discuss about sunrise, sunset and day length. Okay. So, at sunrise the sun's rays are parallel to the horizontal surface. Okay. So, if this is the case, if we take this earth, so when sun is here, okay, sunrise is taking place, this will be something like this, right. So, this is something like parallel to the horizontal surface. Okay. So, under the conditions, on angle of incidence will be, so for this sunrise, angle of incidence that is theta or theta I can write theta or theta I, or say maybe theta z, okay, will be 90 degree, because this will be 90 degree. Okay. So, for sunrise the sun's rays are parallel to the horizontal surface, and hence theta or theta I or theta z is equal to 90 degree. Okay. So, if we substitute this value in the original equation A, which is functions of all the angles. So, what we will get? We will get something like cos theta I is equal to 0, which is equal to cos of phi, okay, then cos of delta, and you have cos of omega s plus sine of delta and sine of phi. Okay. So, how we can simplify now? So, you can take sine del sine phi in this side, and then we can keep cos of phi, cos of delta, cos of omega s in other side, and we want cos of omega s, which will be minus sine delta sine of phi, and then we will have cos of delta, we can interchange, which is multiplicative, and cos of phi. So, this part sine delta by cos delta and sine phi by cos phi is nothing but tan delta and tan phi. Okay. So, now cos omega s is cos inverse of tan delta and tan phi. Okay. Right. So, we can calculate what is omega s, which is nothing but our angle. So, what we have calculated, this is our angle. Okay. So, this expression maybe we can write z, right. So, this angle between the sunrise and sunset will be how much? So, this angle is 90, and again sunset it will be 90, right, it is 90 degree. So, if it is omega s for the sunrise from here to here, then it will be just twice omega s. Okay. So, the angle between the sunrise and sunset will be 2 into omega s. Okay. This will be 2 into cos inverse of minus tan of delta tan of phi. Okay. So, this may be you can write equation equation number GH I can write here. Okay. So, since we know this 15 degree of our angle is equivalent to 1 hour then what we can write, the duration of the sunshine hour will be. So, if we represent that T d, this will be 2 by 15 cos inverse minus 10 delta, then 10 phi. So, this is the duration of the sunshine hour. So, if we know delta, that is declination and latitude of a location, then we can calculate what is T d, which is nothing but duration of the sunshine hour. So, this is very important findings. So, by using these equations we can calculate the duration of the sunshine hour. So, what we have discussed in these slides, we tried to calculate the day length. So, while doing so, what we have done angle of inclinations is 90 degree for sunrise and sunset. So, if we substitute the value of 90 degree here in the cos theta, cos I, so we can simplify this, and finally, what we can calculate is the hour angle for sunrise, and same expression hold good for sunset as well. And also we know this 15 degree of hour angle is equivalent to 1 hour. So, this knowledge we can apply and we can calculate what is the duration of the sunshine hour. So, as per calculation it is found to be something like this, T d is equal to 2 by 15 cos inverse of minus 10 delta multiplied by 10 of phi. So, let us summarize here about this, and in the next class we will discuss some of the numerical problems related to the content we have covered in this present video. So, thank you for watching this video.